Hi guys, and welcome back. Today we're going to talk a little bit more about chords and what happens with them in circles. So today's date for this lesson is Wednesday. That's the 22nd of April. And let's get started. First of all, you have a do now problem. This is a review question based on the material from yesterday. This is what we would have done in class. I decided to just leave it on here because it's a good practice problem. If you want to shut this off and try it yourself first and then come back, feel free. All right, here goes. They told me this entire triangle has a perimeter of 60. They also tell me that GB measures 17. GA, that's this entire side over here, is a grand total of 27. And EA is labeled with a 2Y. And so, based on what we know that if this piece here is 17, then another tangent drawn to the same circle from the same point must match that. So this piece has to be 17. And then they told us that this entire piece, this one plus this one, equals 27. So to figure out how big DA is, I can just take 27 and subtract 17 and get 10. And so now I know that DA measures 10. Now the first thing that they actually asked me for was they asked me for the value of Y. So to figure that out here, I realized that from A, I have two tangents drawn to the same circle from the same point. So AD and AE have to be the same as well. So that means I know that 2Y is equal to 10. I can divide by 2 and figure out that Y is equal to 5. So that was the first part of my question. I now have my first answer, Y equals 5. Now from there, I'm supposed to keep going. So I know that this entire triangle has a perimeter of 60. And I now know that these two pieces both measure 17. And these two pieces both measure, well, this would be 2 times 5, which should be 10, and it is. So these two both measure 17, and these two measure 10. So what I can do here is I can subtract all these parts that I know from 60, and then, because these two segments are both coming from point F, two tangents to the same circle from the same point, I know that these two have to be the same as one another. And so what I can do here is I can take that 60, I can subtract the stuff that I know, which is 17 and 17 and 10 and 10. If I add that all up, that means I have 60 and I'm subtracting 54 from it, which means that there are 6 units that have to be split up evenly between BF and FE. And so I would then take that 6 that I just got and divide it by 2, and that means each one of these pieces, BF and EF, must both equal 3. If you don't trust yourself, you could go back now and do a quick check and make sure that the whole triangle does have a perimeter of 60. And sure enough, even just to do it mentally, 17 plus 3 is 20, 17 plus 3 is another 20, so 20 plus 20 is 40, 50, 60. And you could do a quick check like that and just make sure you did the problem correctly. Okay, before we get to the last kind of arithmetic kind of problem that we have to do with this, there are 2 quick little rules that we have to go over. And those have, something to do with chords and circles as well. So the first one is that if you're in a circle, congruent central angles will have congruent chords. In other words, if these 2 angles in here are congruent to each other, it would follow that the chords that they are cutting off, which would be AC and BD, they would have to be congruent to each other as well. So I could say that if I know that angle AOC is in fact congruent to angle BOD, then it follows that segment AC, that's the chord, must be congruent to segment BD, that's the other chord. So if you have 2 congruent central angles, then you have 2 congruent chords. And then in addition to that, you notice this other little note here, the converse is also true. That means it works in reverse. So if you know that the chords match, you are allowed to then conclude that the angles match. And then we can talk about the second rule that you have to deal with there. And that tells us that in a circle, congruent arcs have congruent chords. So in other words, with this one, if you know that the arcs around the outside match, so if AB out here is the same as CD out here, if arc AB is congruent to arc CD, you are then allowed to conclude that these segments in here, these chords that are being cut off, must be congruent to each other. So chord AB must be congruent to chord CD. You'll notice there's a converse statement there as well. If you know the chords match, then the arcs that they're cutting off would have to match as well. The neatest thing about this is that when you put these two together, you can then draw the conclusion that if you have congruent arcs, then you'll have congruent chords. Then because of the last rule, you will also have congruent central angles in here. So as long as you have one of those pairs of things congruent, all of it's congruent. So those are just a couple of interesting facts having to do with chords and circles that we mentioned again here. Okay, and then we're up to the last part of today's lesson, which is the main part of the actual work that we have to do today, and that's Rule 3. And what Rule 3 tells us here is that if you're in a circle and you particularly have a situation where the diameter, it has to be a diameter, is perpendicular to a chord, then it does something really cool. If the diameter is perpendicular to the chord, that means we're making right angles in here, then it bisects both the chord and its arcs. So what that means is, in this particular problem, if diameter DC is perpendicular to chord AB, then where this diameter hits this chord, it breaks the chord into two congruent segments. So I can say that AE would be congruent to BE, and it also bisects the arcs that are created. So this chord here is creating one arc up here on this side from A to B. That means that arc has been bisected, so I'm allowed to say that arc AC is congruent to arc BC. In addition to that, I can look at the other arc, the arc that this chord is leaving below it, this great big gigantic arc down here from A through D over to B. In that case, this arc on this side would be congruent to this arc on this side. So arc AD is congruent to arc BD. Now, probably not surprisingly, the piece of this that we end up using the most is the first little piece of information, that the chord itself is actually bisected. But it's worthwhile to know that the arcs are bisected as well. Now, the other thing I do want to mention before we get to the problems that have to do specifically with this is the fact that the rule from yesterday still works. So it is still true that because these are two chords technically crossing each other, one of those chords happens to be a diameter, that part times part is still equal to part times part. So there may be certain problems that you'll see on the homework or on the review at the end of the week that allow you to use the two rules together. The fact that these have to be congruent to each other and part times part is still equal to part times part. All right, so moving on, let's do a couple of sample problems. These are the more common kinds of problems for you to see with this situation. They tell us here that in circle O, DOE is a diameter. That should really have a segment above it, so I'm going to write that in. DOE is the diameter, and they tell us that DE is perpendicular to chord AB at point C. So again, all of these should really have segments above them. But the important thing here is that one is perpendicular to the other. So that means that AC in this picture has to be congruent to BC, because this diameter is perpendicular to that chord. Now, the other thing that I'm hoping you're seeing already is that by drawing in the perpendicular symbol in here, that's also drawing our attention to the fact that these are two right triangles. And if I were in class, I'd be asking you guys to come up with this information, but realize anytime you have a right triangle, you are allowed to apply Pythagorean theorem. So that's actually what's going to help us to do most of these problems, that good old Pythagorean theorem. And in case anybody just needs a quick review, Pythagorean theorem is when we say that a squared plus b squared is equal to c squared. And of course, that only works in a right triangle where a and b are the legs and c is the hypotenuse. So in this problem here, if I continue reading, they tell me the length of CO is 3. So this piece in here measures 3. And AO, this piece over here, measures 5. And they would like us to find AB, which is this entire piece here, and CD, which is this piece here. Well, bad news first. I can't find AB all at once. There's no way for me to find this entire thing. But if I focus on just half of my picture so that I'm in a right triangle here, I can use Pythagorean theorem, or for some of you, you might remember your triple, to figure out how big this is. And then we know that this piece and this piece are the same. So for starters here, I'm going to use that little triangle. I'm going to redraw it here just so you can see what I'm talking about. I'm going to use that little right triangle, which is AOC, with the right angle here. If this piece over here measured 3 and this piece measured 5, and I need to know how big AC is, I can go back to my good old a squared plus b squared equals c squared, allowing me to see that 3 squared plus x squared is equal to 5 squared, which means 9 plus x squared is 25, which means x squared is 16, which means x is the square root of 16, which is 4. So I know that this piece from A to C measures 4. If that piece measures 4, and we just learned that this would be bisected, then this piece also equals 4. So the first thing they want me to do is find the length of AB. AB would be 4 plus 4, which is 8. Now the second part of the problem asks me to find CD. This is going to involve some serious thinking and an application of the rule from yesterday. So here's the deal. They told us in this problem that AO is 5. It should be obvious that AO is a radius. That means all radii of this circle are the same. So this radius from B to O would be 5, and this radius from E to O would also measure 5. So they're asking me now, I'm going to use a Y because I already used X down here. They're asking me to figure out how long CD is. CD is this piece up here. Well, this is going to bring us back to what we learned about yesterday. So what I'm going to do is I'm going to redraw this picture with just the parts that I need. I have a circle, and basically I have a chord that's meeting a diameter. Yes, they happen to be perpendicular, but for the purposes of this part of the problem, all I care about is the fact that they are two chords, technically, that are crossing each other in a circle. So the two parts of this chord are 4, and the bottom part down here, which takes me from, let me see if I put a brighter color in here, from C all the way down to E is 5 plus 3, which means the whole bottom part here measures 8. And they would like me to figure out how big CD is, which is this piece up here. And this brings us back to the rule from yesterday, which is that good old part times part is equal to part times part. So in doing this problem, that would allow me to say that 4 times 4 is equal to 8 times x, or in other words, 16 is equal to 8x, and then x must be equal to 2. And that's CD. Oh, I used x. I labeled it with a y, so I'm just going to go back here and fix that. Back on this problem, I had called this y. So I'm going to call all of these y, 8y, 8y, and then y is equal to 2. So since CD had been labeled with a y, I am going to say here at the end of my problem that CD is equal to 2. So there's one answer, and there's the other. All right, and then we have our last problem here today. This one goes and pulls out some other review things from way in the past. It's just a little more challenging that way. But let's go ahead and see what we can do with it. They have told us that angle RTS is 50 degrees from R to T to S. We're talking about this entire angle here. So what you have to realize with that information is that's a central angle because it's going to the center, which means since this is a diameter perpendicular to a chord, again, these should have segment lines over them. You can write those in on your lesson if you'd like. That means that these two arcs must be congruent to each other. So if this angle is 50 degrees, that means this arc is 50 degrees. And since we know it's been bisected, each of these arcs then must be 25 degrees, which means that each of the central angles making them must also be 25 degrees. So when they ask me for the measure of angle R and the measure of angle S and so on, I need to do that first. Now, I have some choices. They tell me that this is a right angle in here. It doesn't look like it's drawn to scale exactly. That's okay. They do that on purpose sometimes, especially on the SAT. Questions are not always drawn to scale, just to throw you a little bit. Try to ignore it. And then that means you realize that each one of these is 90 degrees. So with that information, you can focus on either one of those little baby triangles and you see that R and S are going to be congruent to each other. If I focus on one of these baby triangles in here, then I can actually just go to the fact that the whole triangle is 180. I can subtract the 90 and I can subtract the 25. And if I do that, then this must be a 65-degree angle. So angle R is 65 degrees and angle S is also 65 degrees. Now, for those of you who would like an alternative, I'm just going to explain something else here. You don't have to write it down. You also could have realized that RT and ST were both radii of the same circle, so they're congruent to each other. That would have led you to realize that this must be an isosceles triangle. And then you could have done 180 minus 50 and divided by 2. And you would have ended up with exactly the same answer. It's just a different way to do it if you're interested. All right, then we're going to focus the rest of our problem on the lengths of chords. They tell me here that PT equals 8. PT is a radius of this circle, so ST is also 8, and RT is also 8. Then they tell me that UQ measures 3 inches. That's this little piece out here. So for starters, if that's 3, then UT, this little piece in here, would have to be the rest of that radius that's going from T to Q. So UT, the first thing they're asking me for there, that must measure 5. And then they want the length of ST. Well, I already labeled that on my picture. ST is another radius, so ST must be 8. The last part of this problem is that we have to figure out how long US is. And US is this side of that triangle. So if I come over here and just focus on that little piece, I have a right triangle there where one side measures 5, the hypotenuse measures 8, and I am looking for the other leg. And so I'm back to Pythagorean theorem here. It's a little annoying because it's not a pretty one. A squared plus b squared equals c squared is going to become x squared plus 5 squared equals 8 squared, which means I'm at x squared plus 25 equals 64. When I subtract that 25 from both sides, I'm down to x squared is equal to 39, and then x would be the square root of 39. And there really isn't anything else that I can do with that, so my final answer there for US would be the square root of 39. Interesting little just math tidbit review thing is if for some reason they wanted you to find RS, that would be 2 of these, so that would be 2 times the square root of 39. Just thought I'd throw that in. All right, I hope that made sense. Homework tonight is going to let you practice those a little bit using that picture a whole lot. So remember your Pythagorean theorem. Remember that all of the radii of any circle all are the same measure, and hopefully that'll help. All right, hope you guys have a great day. I'll see you back here soon. Bye-bye.